Okay, recording, and I'm going to share. Okay, so I'm sharing the screen now. So this is related now to the homework assignment, the third homework assignment, which should be under here, RLHF. So we're trying to understand that whole process of fine-tuning, the whole process of reinforcement learning for GPT models. You guys have this third assignment, which is this here, right? So I've added a few more texts to this homework, and today I'm going to provide a few more examples. So if you remember, you need to, um, implement an RLHF using the TRL library. So that's all I'm asking this semester, to use TRL. Fine-tune with RLHF a GPT to generate text that sounds more like some specific genre of text. Essentially, we've established that you need to get a good BERT reward model. You can use as an example the following, and this is the example that I did last week, if you remember, the phishing and spam example, where we took a distilled GPT-2 and we made it so that it generated more spammy text. Use TRL from Hugging Face to fine-tune a GPT pre-trained model using RLHF. You need to define the problem, find a data set if needed, and use a reward function such as a BERT scorer. Like in the IMDb example, your goal is to make that GPT be better at a specific task. In the IMDb example, the GPT was fine-tuned with RLHF to produce more positive reviews. You will need to demo this project, or also you can replicate any of the examples in the following link. So there should be some examples in the TRL library. Okay? PyTorch is required for this test. All right, so that's the homework. So this link here is got the examples that I've been doing in class, so the TRL example. So this is the phishing and spam example. All of these examples, unfortunately, have been using the older TRL library. All right, so I want you to be aware of that, which uses Python 3 or Python 3.9. So if you want to use the older library, when you have your environment, create a new environment and use that command. It'll give you the old library. If you just do pip install TRL, then you get the new library. All right, so today I have a new set of examples to kind of wrap up the class today of doing RLHF. So in this, I have two. So this one actually is really interesting. This GRPO uses Quen or Llama for RLHF for homework 3. And as you can see here, GRPO, as you start to understand reinforcement learning, should tell you that this is what DeepSeek used. Okay, so this is in fact a super simple replication of the DeepSeek paper. So this uses, it's not exactly chain of thought, but it is using math solving. Okay, so I tested this script and it does work. The only problem that I ran into is that I ran out of memory. So my CUDA out of memory for what I was trying to do. I did not want to switch the GPT to distilled GPT-2. And instead I was trying a very, very small, you can see it here, a very small, where do I have it? Here, Quen 0.5 billion, because I'm trying to use a model that has already been fine-tuned for instruction, to take instructions. So, and I ran out of memory. I have a 2080 Ti, an RTX 2080 Ti GPU. I'm hoping that's the problem. I'm currently trying to run this on the Scholar, where we might have a little bit more powerful GPUs. So I'm going to run it again. But I wanted to make you aware, if you're interested, that this is somewhat of a replication of DeepSeek R1, or at least the base model. But it's something using GRPO because this as we will learn later on, like PPO, this has already been implemented on the TRL library. A few differences is that this uses the latest TRL library, so make sure to note that. So here, and these are all the commands for installation. I tried this with Python 3.9 and it should work. So all of it ran. I was able to load the library. You have your prompts and everything. Notice that it says that it's doing some reasoning here. So unfortunately, like I said, I've not been able to run this fully, so I don't know the performance, but this is the code that I have so far to replicate DeepSeek. Notice how one difference is that I mentioned in the previous lecture that the state of the art used to be that you would have a GPT and you would provide feedback through a BERT model. So two neural networks, as we will continue to learn. And this is related to your homework 2, which is finding a BERT. However, what I find really interesting is the DeepSeek work that just came out 2-3 weeks ago. They only have one neural network, the GPT, and the rewards, instead of being a BERT, are just heuristics. So you can see they're like these functions here. So this is down here, sorry. These are the reward functions, which are basically heuristic reward functions. So that's really interesting. The data set that this uses is GSM-8K, this math data set of problems and solutions. So as I said, this code should have a lot of the basic ideas to replicate DeepSeek, and it is still consistent with the homework because the goal of the homework is to take a GPT and use reinforcement learning to fine-tune it, right? So if you guys are interested, you can play with this. Just keep in mind that, I ran out of memory, so you do need somewhat of a powerful GPU. Notice that the batch size also is 1. So it is at here somewhere. Per device trained batch size is set to 1. So we can't decrease that any further. All right, but that's an example. Another example of homework 3. So distilling with a GPT-2, as we did last week, GRPO, which is DeepSeek paper. And then here I have another set of examples. This is MathGPT. So this is based on work by Noah Ford. He worked on this last semester, and he essentially would start with a GPT-2, apply something called SFT, which is supervised fine-tuning. So essentially, he is not using reinforcement learning. He is just fine-tuning it, as we normally would. Any model, just, it's say we have model with images, and then we just give it more images to fine-tune. So this one I was able to replicate successfully with GPT-2. Llama 3 is a bit too big for my RTX 2080, unfortunately, it seems. I haven't updated the software on that card, so that could be the issue. Like an updated software might be faster. But anyway, you can use this as your reference. So in this case, you start with the GPT-2 and you fine-tune it, and then it produces a fine-tuned GPT. Then you can take that fine-tuned GPT into your PPO RL. It'll further fine-tune it and produce, a final GPT. So currently, the idea is that the approach is to take a pre-trained GPT, fine-tune it with some data, and then apply reinforcement learning to it. Okay? Does that make sense, guys? So, and then you can see the inference is actually two separate functions. So they just essentially read in the trained GPT and you start giving it problems. So let's take a look at, for instance, this one. This is just the SFT one. And this is all the code. So you use transformers, of course. You have some functions for dealing with formatting, quantization, the data set that you're using. The model is SFT GPT, GPT-2, and you just load your model. So here you load the fine-tuned model. You also load the tokenizer, and using, of course, transformers. And then you create this object called a pipeline for text generation. And you give it the model that you just fine-tuned. And once you have a generator, you can start generating text. So essentially, you grab a prompt from the data set, give it to the generator, and the generator will try to solve it. So as you can see, my results are not the greatest, but the idea is these are math problems. So you take, for instance, a robe takes 2 bolts of blue fiber and half that much white fiber. How many bolts in total does it take? So that's the problem that you give the model, and then it should give you an answer such as this one. Does that make sense, guys? So you have a question here, and then you have the answer. Now, I trained these with GPT-2 and the distilled GPT-2, so I don't expect it to be that good, but it'd be interesting to see if you guys could use, for instance, if anyone chooses to do this, a llama, right? Like a llama 3.2, and then would that be better? The issue, of course, is memory. It's gonna, it requires a big, powerful card. Does this make sense, guys? Any questions about this? This is just the inference part. All right, let's take a look at the fine-tuning and so we'll wrap up with that today. So this math model, right? We have essentially here's a math GPT. We're going to use supervised fine-tuning. The data set is GSM 8K, Python 3.8. This is using the old version of TRL, and there's the installation command for it, pip install and the version. You load your libraries, and this is for formatting. So format dataset prompts to match the style that we want. So you'll just take all your text from the, you get it here, and you're just going to modify it to have these things like question and answer so that the prompts are a little bit more clear. Then you create the training arguments here. So training arguments from Hugging Face. So you're going to say the output directory is SFT GPT-2. That's where the fine-tuned model will go. The logging strategy is for epochs, and number of training epochs is 3. Okay. Then you are going to, this is essentially trained on my GPU. The model config is going to be GPT-2. So actually, this must have ran with just regular GPT. So maybe it was my PPO that required distilled GPT-2, which makes sense because with supervised fine-tuning, you don't have 2 models, right? So you don't have a GPT and a BERT kind of helping each other out, 2 massive models. Fine-tuning is just taking the GPT and training with the data. So now that I remember, this is just the regular GPT-2 from Hugging Face. So yeah, so this is essentially the torch data type that we want. Okay. And then these are the model arguments. So just data type, the GPU device that we're supposed to use. Then we invoke the tokenizer from pre-train, whatever the model is, downloads the tokenizer. The data set that we are fine-tuning on is GSM-8K, which, like I said, I think it's a set of high school math problems, as you saw, problem and the solution. That data set is split into train data set and eval data set. So keep that in mind. So you fine-tune on the train set. Okay. Everyone with me? And so yeah, so this work was done by Noah last, and I replicated it. He did an excellent job. Then as we can see here, the key idea with Hugging Face is you use these trainers. This is the part that we need the theory for, because as you can see, there's a lot of abstraction here and you don't really quite know what's going on behind the scenes. But for us to replicate this is probably the best way. So we use an SFT trainer instead of a PPO trainer or whatever it was. You just specify the model, the arguments, or configuration parameters, the tokenizer, the formatting function, etc. So it just takes all of this, the train and eval. And then I trained this model. I can't remember, honestly, how long it took. But I ran this. You can see training loss did go down a bit. Okay. And essentially, once I finished training, I just saved the model. You guys see that? And then basically that's what I showed you before with the inference function. So the inference function just loads this model and performs inference. All right, so in the last 10 minutes, we're going to cover the last part of it. So that's how to do just fine-tuning. You only have one model there, so maybe here you can give it a Llama 3 or something big, and hopefully get good results. Actually, fine-tuning is very useful, and you can if you have really good data, it can actually produce very good models. All right, so the next example is, as you can see, we do inference on the PPO of distilled GPT-2. So that's going to be the same as the previous inference. So we really just want to concentrate on this step. So notice this script is called PPO after SFT. Click on that one. All right, so here I still use this is RL reinforcement learning through human feedbacks, RLHF with PPO, okay? So this is going to involve some kind of a reward. So you can see we have old TRL. We use transformers in the TRL library. We got our PPO trainer. Our PPO config, as you can see, I had to use here a distilled GPT-2 as the GPT-2 that I had in there was too big. GSM-8K is the data set, and the reward model is this one that Noah found, all mini LM L6V2. So he used that for the rewards, I believe. All right, so that's the learning rate. The mini batch is 16. I think it was 32, and I brought it down to 16. You can see I wrote 32 here. I meant to write it here. That was a mistake. All right, so there we have it. So number of epochs is 5. So once you do that, the same idea as before, you build a data set, build data set for PPO training. Inputs are pre-encoded for use during training, so we can use this function to modify the GSM-8K data set. Here, remember, we had talked about how RLHF works. we instantiate the model, but we also have a reference model. So this essentially just doubled the amount of memory that you need because you have GPT-2 and now copy of GPT-2. Remember that we want to have two so that we use something called the Kullback-Leibler divergence metric. We just don't want the model to deviate too much from the original. Notice that this code also uses quantization, which is really fun and I would say really cool. So what this means is that the variables, if they were size 32, they are effectively made into size 16. There is apparently even a quantization to size 8, but you just have to have like very specific libraries of, I think, Torch and maybe even CUDAs. So that's something that requires some adjusting of your specs. But obviously, if you have quantization to something like 8, it means that you're consuming less memory. So it's really important and helpful. We create the tokenizer here for our distilled GPT-2, build a data set, essentially create now, instead of a supervised fine-tuning trainer, we create a PPO trainer. What is a PPO trainer? Remember, it's a topic in our reinforcement learning. We've started with Q-learning, and we're going through those value-based reinforcement learning mechanisms, and then we're going to switch to the policy-based methods, and one of them is PPO, but it's essentially a little bit like the Bellman equation. Think of it that way. So it's like the thing that allows you to learn, and it's in relation to the rewards. That's actually, now that I think about it, the reason why I initially wanted to introduce Q-learning first. So let me actually make that connection. What I mean by that is, you know, in this example of reinforcement learning, right, when we discuss the code for Frozen Lake, we are training for the table, but to learn the values of the table, oh, and this is actually, sorry, I need to go to the other thing. This one. So in the code, in this for loop, right, the way that we learn the values is, you know, through the Q table. That's kind of like the learning algorithm or learning function. In our approach here, in this example with MathGPT, that's the similar thing to the Bellman is PPO. It's how we learn. It's another technique called proximal policy optimization. So it's one of the topics that we will discuss the background and the math of it. Okay? So then we use the PPO trainer, provide the config, the model, the ref model. Notice that 2 models are now provided. The tokenizer, and so on. And then here we set up the device, which is CPU or GPU. This is to get the reward, a reward function. So if you use a heuristic reward, for instance, or the BERT model. And then this should be the training loop, essentially. So we train, we provide, notice, you know, we grab from data loader the data, the query tensors. The query tensors go into generate of the model, PPO trainer, that produces a response. And then that, you know, gets processed further. But essentially then, once you have a query and a response, and you have rewards, that is given to the PPO step that performs the proximal policy optimization process. And that gives you that's how you provide the feedback to optimize the weights of the model. All right. So we will have to come, that's a big topic, how that works. So we'll definitely come back to it when we discuss like the background. But for now, this is the implementation of PPO with TRL and how it works. And then, of course, it does the training. So this, I wasn't very efficient how I printed this out, but it did train until the end. Let me grab that. So you can see it finished. Yeah, it finished over here. And once it finished, I just saved the model. And then, as I said, once I have the model, I just used this inference function, PPO, where I read the model and basically given questions, I start producing answers and so on. So this one unfortunately used GPT-2 distilled, so I don't know how good that was, but I wanted to run the whole pipeline. If I figure out how to get more memory on my GPU, or if you guys have more powerful GPUs than I do, or Scholar is, feel free to run this with a normal GPT-2 or Llama, and it'd be interesting to just compare the results. Does that make sense, guys? All right, so I'm going to stop the recording here.